Hello everyone. Welcome to the Unity workshop. So a bit about myself. I'm the president of NUS GDG, and I've been the Unity workshop head for 4 semesters running. I won't say I'm very good at this, but I'm a little bit experienced. So today we'll be going through Game AI. And before we get started, please scan this QR code for attendance. Okay, good. Are we all done? Right. So, yeah, before I start the presentation, does anyone have an idea of what Game AI is? NPC behavior, yes. Anything else? Maybe from the games that you've played before, you can think of some concrete examples of what showed up. Find your character. Okay, yes, that's the behavior of probably certain allies or friendly characters in games that you've played before. Yeah. Anything else? Maybe? How your opponents move? Yes, enemy move sets and behaviors are also included in Game AI. Yeah. So Game AI is just a very broad term, but generally we used to refer it to like intelligent behavior for non-playable characters. So this could be your friendly units, enemy units, or even just random neutral animal creatures in the game. If you've played like games like Minecraft before, you have friendly units like Villager that also has their AI. You have pigs, cows, and sheep. All these animals also have their AIs. Also, all the enemies, for example, zombies, creepers, they have their own separate AI. As you can imagine, that they have separate behaviors, different behaviors as well. So the term game AI generally consists of different prospects of things, and the most general one is behavior, how they act, how they move around, for example, what kind of logic they use in order to decide what they want to do at this particular time in the game. There's also pathfinding, which is kind of a term that is used for these non-playable characters to move around the map. This would be very useful, especially in say open world games or sandbox games where you have a very large area with uneven terrain where your non-playable characters will have to move up and down and navigate around the area. So there's pathfinding. There's also decision making. There are times where, say, if you play the Monopoly game on your phone before, sometimes when you ask for a trade order, the enemy AI would, think if this order is valid. If this trading option is valid, then they'll make the decision whether or not to take on your offer or not. There are also other games, for example, if you played Civilization before, you would know that communicating with other civilizations and then giving them their envoys, they can choose to accept it or not. And this is part of the decision making as well. So you would have to govern all these kinds of things through like game AI, some kind of algorithm or some kind of calculation that triggers whether or not they would do this decision. There's also adaptability. Now this is quite new, but in recent years with the rise of like more intelligent AI, more compute power, game AIs have been made to adapt to surrounding areas. They've been made to make different decisions based on what is around and what kind of flags that the player has made before. So this is to adapt to the player's decisions and to the surroundings of the area. If you've played games, AAA games like Assassin's Creed, then you would know that sometimes the AI just takes up nearby stuff and then try to hit you with it, for example. So yeah, it's this kind of adaptability that makes games more interesting and immersive to play. There's also the game balance aspect to it. If you make your game AI too difficult, like Elden Ring or the Dark Souls series, then a lot of people would probably not want to play your game. Like there's this very niche kind of genre that you are going for. So if you want to make your games to be targeted towards more people, then you would have to tone down your AI so that it's less difficult and more people would enjoy actually playing. Maybe you can also have like several difficulty tiers for your AI, and it would cater to all the kinds of different players that want to play your game. So yeah, it generally consists of these five aspects, and I think there are two general common implementations for a game AI. There are more, but these are the two most common ones that you can find in a lot of the games. The first one is a finite state machine, and the second one is a behavior tree. So, what is a finite state machine? Anyone here heard of the term before? Or probably heard of the term state pattern before in software engineering? So, this is exactly it, but we usually refer it to FSM in game development because the way how this term came to be is that we define a bunch of states and then we define the transition between states. And since there's only a finite number of states that your AI would want to have, we name it a finite state machine. So when you're trying to design a finite state machine, you first need to define the states for your AI. For example, your AI can move around. It will probably aggro on the player when they see the player, and then they would chase the player, and then when they're close enough, they'll unleash their attacks. If their skills are on cooldown, they'll retreat. So these are the states that you would want to define first when you're designing this AI. You define, of course, the behavior, which is part of the state. When they're aggroed on a player, they want to chase them. When they're close enough, they want to attack, and what attacks they want to use probably depends on what attacks are available for them and what attacks are more suitable for this particular scenario. And you also want to define the transition between states. What are the conditions that lets you transition from one state to another? For example, if I'm designing a normal enemy monster, they would probably start from like an idle state. And then if the player comes close to it within a particular set distance, then they would aggro and then they would turn around and chase the player. So these are the transitions that you want to define so that the AI looks more intelligent. If you've used Unity before, whatever that I said just now might sound familiar. Anyone knows what this is? Yeah, this is the animator, and this follows the state, a finite state machine as well. So every single animation clip that you put into the animator, there are nodes, and then you define the transition between each nodes. For example, you can go from any state to bounce in this particular example, and then you would define these parameters that will decide which transition gets triggered at what time based on the parameters based on the values of the parameters at that given moment. So yeah, this is a finite state machine. Obviously, if you made it this complicated, you would probably want to rethink your life decisions. But yeah, I think this is valid. So let's go into a quick example. What is this? Anyone knows what this is? You don't play Minecraft. Okay, but have you heard of this thing before? Have you seen this thing before? Okay, this is a creeper from a Minecraft. So, very quick description of what it is. Basically, it's a monster that spawns at night and then it walks around. And then if it sees a player, it moves towards the player. And then if it's within 2 blocks distance, it will start exploding, and then when it explodes, it deals tons of damage and it destroys all the surrounding area. This is probably a newbie's worst nightmare because a lot of people don't know how to counter this guy, and it destroyed a lot of houses before. So, as I mentioned, it spawns with an idle state, and then if the player gets close to it, it moves towards the player, and if it's in proximity, it explodes. So, the way how this can be modeled as a finite state machine is that we first define the four states, which is idle, patrol, it moves in a random direction, aggro, it moves towards the player when the player is in sight or range, and then it explodes when the player is in proximity, which usually is within a 2 blocks radius. So now that we defined how the states of this creeper is going to be, we can draw this out. This is what we call the state diagram. So it always starts with this idle here. I think I can change this to a laser pointer. It starts with idle, and then after every X seconds, which generally is defined by the difficulty level of the game, it will go into patrol state, which lets it move in a random direction for a set amount of time, and then it stops and it goes back to the idle state once it's done. So this will keep on repeating until the creeper dies or until the creeper enters a different state. So if it's in an idle or patrol state, once the player is in a set distance, which I think 30 is an exaggeration, it doesn't really detect you from that far away. But if it's within this distance, say we define it as 30 blocks, once it's within this 30 blocks, it will enter the aggro state if it is currently in the patrol or the idle state. And then when it's in the aggro state, it will move towards the player, in which, if it goes within a distance of 2 blocks, it will enter the explode state where it starts self-destructing. There's like a 1 second delay when it starts until it actually explodes. So during this time, if the player moves out of the distance, it will go back to the aggro state and chase the player again. So as you can see, this particular mechanism here is to allow the creeper to not explode when the player is not in range. Whoever designed this thing has a very bad humor because he really wants the player to die by making sure that the creeper doesn't explode if the player is too far away. Yeah. So after you design this, you can then convert this into code, which I will show you how you can do a very naive implementation of a finite state machine later in Unity. But before we go into code, we would have to do a very quick activity on designing this finite state machine. So you can probably take out a pen and paper and draw out the states and the transitions, and yeah, just a very quick hands-on exercise. Probably takes 5 minutes or so. So this is a zombie from Minecraft. Obviously, this is not all the behaviors of this particular it's called a mob, right? Not all the behaviors to this zombie in Minecraft, but this is generally the core behaviors that it has. So it randomly patrols around the area every 10 seconds, for example. It moves towards the player when the player is in sight. It attacks the player when the player is in reach. And upon spotting the player, it will call for help from nearby zombies. And when killed by the player, it alerts all nearby zombies to go to the player's position. Hmm? The last one, no. But it does call from help for nearby zombies and hard difficulty. can see that most of y'all drawn it out, and it looks pretty good, pretty neat. And I actually don't have a sample here because, well, the way how you interpret the state machine can be different, and there's no like one correct implementation even for the same behavior. So yeah. Okay, yes. So now you can open up the Unity Workshop repository, and as you open it up, you should see the sample scene, which I have set up 2 capsules and a plane in 3D space. Very simple stuff. So the green capsule is the player. The player already has a very simple movement script attached to it. You can take a look at it, but basically what it does is WASD to move, and then if you hold shift, then it's going to start running, which moves in faster speed, and then if you press spacebar, it's going to jump. So yeah, you can take a look at the code if you want to, but it's not that complicated. There's also the enemy script with the enemy object, which is the red capsule, which I've also added a very simple script of it, which is just a naive implementation of a finite state machine. So the way how this works right now, as I go through the code with you, is that on every update, it's going to first check if the player is within the aggro range. So this is going to be the distance check, and we want to be able to aggro to the... Right now, there's like only very less states. As you can see here, there's only idle, moving, and aggro. So this is very naive, and you probably don't want to do this because it will most likely cause issues if you don't do this correctly. But right now in this naive implementation, whichever state I am currently in, I'm going to set myself to aggro if the player is within the aggro range. Then I'm going to do a switch case here based on what states I'm in. I'm going to execute the behaviors for each state. So the idle state is just going to be me and idle, and then if I can currently move, which is the countdown for the patrol, then I am going to select a random direction and then move in that particular direction for a couple of seconds. This move state coroutine just sets my state to move and then sets it back to idle for 2 seconds, and that's just what it's going to do. In moving, in this execute moving, I'm going to set my velocity towards this particular direction, and yeah, I'm just gonna print it out. I mean, this debug statement is here for fun. Then when I'm in the aggro state, I'm just going to do this check, which is to check if the player is currently outside of my aggro range plus 1 meter, plus 1 unit. This is, for example, this is just like an additional heuristic so that it's not going to stop immediately after I exit the aggro range. It has like some extra distance in between the switching of states. I'm going to set my state back to idle. If not, then I'm going to rotate my my enemy to look at the player, but it's not like you're gonna see it because it's just a primitive capsule, and then it's going to move towards that particular direction. So let's put this into play and we're gonna see how this works. This is going to be in first person so that it makes it much easier for you to control the player. But basically, as you can see, I can move towards it, and then once I'm in this aggro range, it starts moving towards me. as you can see now, because the enemy has the same movement speed and it feels like it's not moving, but you can see on this side of the screen that that is actually moving towards me. And if I try to run out of its aggro range, which I should be able to if I sprint, it will start moving away from me again, because now it has entered the idle state and it immediately goes into patrol. So yeah, this is just a very naive AI implementation. So the task for today, right, the hands-on task for today, for the rest of this workshop, is for you to modify this naive implementation so that you add your own behavior to the AI. It can do anything. For example, if you feel like you want to add an attack state to it, or you want to add like a self-destruction state to it, or anything, you can try your creativity and probably do something with it. So before I hand the time to you to try things out, there are some tips and tricks that I do want to say. So the first one is that if you want to do line of sight checks, so for example, you don't want this AI to be this stupid, okay? It's like right now I'm just checking if it's within range, right? If you don't want it to be this, it feels not natural, right? Like if I walk behind the enemy and then it still knows that I'm here because I'm within this range, it doesn't seem logical. So the way how we can try to avoid doing this unnatural thing is that you can use line of sight checks, which generally is done by ray casting or box casting. So ray casting or box casting, anyone of you haven't heard of it before? Heard of it, right? So the way how you would implement this is that you would either do a ray cast to transform forward, which only checks for this one particular direction, which is bad. But if you use box cast, then you can do a larger line of sight. So this kind of has like this FOV perspective that you can check. So it would just be like this one area in front of me. Unfortunately, if you try to do like the view frustum check, so if you look at the actual camera itself, you realize that where's my camera? Cannot see the view frustum. And to turn on like something here. No. I don't remember where the gizmos is. Oh no. No. Okay, but generally speaking, when you actually look at how we look in real life, it's not like we look at one box, right? Your vision kind of expands out. There's like a field of view kind of thing. Unfortunately, with box cast, you can't really do that. And in Unity or even in Unreal, there's no easy way to do this kind of FOV check. There are ways to do this, but if you try to write it out in code, it's quite expensive, and if you do it every single frame, then it is going to impact your performance quite a lot. I've tried writing it myself, but it doesn't really work very well. So, generally speaking, for a very cheap and easy way to do line of sight check, you just do box cast. And if you give it a set enough area, for example, like say if I box cast myself like this in front, then the field of vision is quite similar to how I would be, as long as it's within a particular range. If it's not too far away, then my field of vision doesn't really expand far enough for this box cast to not match it properly. So you can also merge similar states together to avoid overcomplicating the machine. For example, you can merge walking and running into like a one single moving state, and then you just change it with speed modifiers. In fact, this is how the movement script, the player movement script that is currently implemented, I just have a different multiplier for walking and running, and then this is triggered by me having the run state on. Yeah. Then the final tip is that once you start writing very big finite state machines, for example, like whatever this one is, right? It starts getting very complicated for you to track all these transitions just by reading through your thousands of lines of code, as you could imagine. So one of the ways to make this very scalable is that you can use a state transition dictionary. It does induce an additional overhead in terms of memory and performance, but I think this is a good enough way to implement it. So the way how you do it is that you have a dictionary of a tuple of state and string and a second state. So you're trying to transition from state 1 to state 2 right now. And this transition is being triggered by this particular toggle that is stored as a string of information. Now you don't use a string and use like enums. Then you have to define like 60 different toggles. Or you can use an integer number for these kinds of toggles. So this is changeable. It's just that what kind of toggle you want to do. So how you can sort of use this is that once you define this state transition dictionary, you can initialize it with the set of values, which is all the kinds of different transitions you want to add. In this particular example, you would say I would add the idle state to the patrol state in the dictionary with the toggle being say a string called can move. So how I would be able to do this in code, let me just write this out very quickly for you guys so that you can sort of see what is going on. I have a dictionary. Come on. So I have a dictionary of the states to a string and then I'm just going to call this the transition dictionary. So this is sort of like a C# thing, but you can actually initialize the dictionary immediately here with the collection initializer. Wait, how do I do it again? Yeah, something like this. So you initialize a new dictionary here, and then you want to assign this state to it. So for example, I'm going to create a new entry with this curly braces. The first one is a tuple and the second one is the state. So I'm going to transition from the idle state to the moving state right now. And then I'm going to define a trigger for it. In this case, I'm just going to call it like can move. So how we're going to be able to use this is that I'm going to define a helper method, which is going to be a transition tool, for example. And then I'm going to have the string, which is the toggle. And then, as GitHub Copilot, being very smart, has already recommended what code that I'm going to do, is that I want to get this value from the transition dictionary. If there is a value in this transition dictionary, that contains this tuple, which is the current state to the toggle string. Then I'm going to assign this next state to it. Then instead of having to manually assign all these states, now I would be able to change this to is the current state to the moving state. So I'll change this here. Instead of manually assigning this here, I can do this. Transition 2 can move. Then this will immediately toggle this state for me, and I don't need to define all these kinds of logic to manually change the states. I just need to extract it out and put all of it in the dictionary. So you probably don't need it today because, as you can see, it takes some time to figure out how to get it working. But yeah, so this is the activity time, and you can design your own AI with FSM in the sample project. So a quick peek on what we're going to be doing for the next 2 weeks. There'll be 2 more weeks for this AI workshop, game AI workshop. Next week we'll be going through pathfinding and navigation meshes, which is a very quick way of doing pathfinding in Unity. Very happy that they added it to the base engine support. I don't know when they did it, but it's a big W for Unity. And for the week after next, we will go through behavior trees. So we'll be using this new tool called behavioral graph in Unity 6. I don't think it's particularly new, but basically it allows you to define a behavior tree using visual scripting. It's sort of like the animator, but it is much more advanced in that particular sense. So yeah, look forward to that, and I hope to see you next week for the YouTube guys. Yeah, so yeah, any questions before you move on? Any questions? No questions? Good. So thank you for coming.